Okay, well, it's my distinct pleasure to introduce Alex McDonough. He is coming to us from Brown University, and he's going to talk about a higher dimensional Sandpile map. Take it away, Alex.
Thank you. Thanks so much for the invitation. So I'm going to be talking about a higher dimensional Sandpile map. And yeah, I've been working on this for a little while, so it's going to be similar to a paper that I have out on the archive now. I should remember what it's called, but it's like the most recent one that has something to do with something similar like this. But so first of all, I'm going to define orientable arithmetic matroids, which might seem like a scary thing to start out with, but these two words in front of matroids actually makes it easier to work with, believe it or not, at least the way I'm going to be using them. And I also encourage everybody to learn about matroids because they're beautiful. And I'm going to show their relationship to other combinatorial objects, in particular to graphs, to cell complexes, to regular matroids. I'm going to define their Sandpile group. I'm going to give a generalized Matrix-Tree Theorem. So I talked about this briefly in the pre-talk, but this tells you that the Sandpile group of a graph is the same, that the size of it is the number of spanning trees. And we can generalize this to orientable arithmetic matroids in some way. I'm going to construct a periodic tiling of space. Why am I doing that? Well, I'm going to use it to construct bijections. And I have that in quotation marks because they're not bijections. I'm going to show a few pictures and animations that I hope you'll like. And feel free to interrupt me anytime with questions. I usually have a philosophy where if I don't finish the talk, but there's like a great discussion in the middle, that's generally preferable to getting through all of the stuff and having people zoning out by the end of it. So yeah, feel free to interrupt anytime. My goal is to make it pretty approachable. So if there's something that doesn't make sense to you, it probably doesn't make sense to other people, and just let me know. I'll do my best to explain. All right, so let's talk about representable matroids. So a matroid is a pair. There's some set E, and then some subset of the power set, which is the set of bases, and E is called the ground set. So there's some conditions that this B has to satisfy, and they're actually pretty nice, but I'm not even going to get into them for this talk because we only need representable matroids. So the way to get a representable matroid is we start with a matrix. And I'm going to label the columns of the matrix because these are going to be important for us. The ground set of our matroid is the columns of the matrix. So in this case, V1 through V4. And then the maximal linearly independent subsets of this ground set are going to be the bases. So in this case, you can see that even though there's 3 rows, this is actually a rank 2 matrix. And any 2 of the columns are going to be linearly independent except for V1, V4. So this ends up being our list of bases of the matrix. And the size of each basis is the rank of the matroid. For any matroid, all of the bases are the same size. So it's going to be 2 for this example. And if we were just talking about the matroid that's represented by this matrix, all that we know is E, we know fancy B, and we know, well, we know the rank, but that comes from B. So just E and B is enough to give you this matroid, but we can, there's multiple different ways that we could write the vectors that are going to represent it. Okay, so we have this, basically information from last slide, and we're going to add something to it, which is basis multiplicity. So this is kind of adapted from the idea of arithmetic matroids. This is kind of the most nice version of arithmetic matroids, but there's some more generality that you can do that if you read the paper on them, it's Mochi and Didario, they say it more generality. But for now, I'm going to say that since we're working with these representable things, the multiplicity of each basis is going to be the GCD of the determinants of all rank by rank minors when we restrict it to the basis. So if we want to find the multiplicity of this first basis, we're going to take all 2 by 2 minors and find their determinant. So this determinant is going to be 1. This is -1, and this is -2. So we have 1 is our GCD. For 1, 3, it's going to be, we have -1, 2, and 2, so it's going to be 1 again. For 2, 3, it's going to be -2, 2, and 4. So we're actually going to have a GCD of 2. And then the remaining ones, you can see the multiplicity is 3. We don't have a multiplicity for M1, M4 because that was dependent. And we're going to call this triple an orientable arithmetic matroid. And I just need to put in a technical note. So orientable arithmetic matroids were defined by Pagaria, and arithmetic matroids, as I was saying, were defined before that. Usually you define the multiplicity on all subsets of the ground set, but it ends up being useful for what I want to do to just define it on the bases. And when we do this, this is going to be equivalent to requiring the strong GCD property. That's what Pagaria calls it. And that's sort of the thing that makes this definition the same as his also. So if you look at that, it's going to seem a little backwards, but he shows that this is equivalent. So this is what we're going to call our orientable arithmetic matroid, or OA matroid for short. Any questions so far?
So what is making this orientable?
That's a great question. So normally, this is where the fact that I'm using a different definition comes in. The fact that we can write this on a matrix like this means that there has to be some orientation that we can work with. If we had a general arithmetic matroid where we didn't require it to come from a matrix like this, then it would not be necessarily orientable. So orientable is sort of equivalent to representable in this instance, but it ends up that Pagaria defines orientable arithmetic matroids in a more natural way by saying like, oh, you have an orientable matroid, since oriented matroids are also a big thing people study, and an arithmetic matroid, and you have to have something that's both, and you also have to have the oriented part and the arithmetic part interact in a very particular way. And I can kind of get around this by giving this alternate definition, which works when we're requiring the strong GCD property. But yeah, it's a great question because it wasn't clear where orientable was coming from at all.
Okay, so are you kind of using the determinants here as a way of getting at the signed properties that would be coming from an oriented matroid?
Yeah, so if I wanted to have the oriented aspect in it, I could define a chirotope. That's how it's done a lot of times to get an oriented matroid, and have that keep track of the signs of these determinants. It's a little weird because we don't have a full row rank matrix, but if we just kind of cut off a row, then we could have this chirotope that keeps track of the signs. And then it turns out that this is an equivalent way of defining things. This is going to be a big chunk of my thesis that I'm working on right now, is defining exactly how all of this connects together. In the paper that I have out on the archive, I sort of skirt around some of the issues with where the orientable arithmetic matroid part is coming from and where the orientable is to get to the main results. Because this is one of those things that it takes a whole lot of time to say things that end up not being too complicated. But yeah, there is a way that we get an oriented matroid and an arithmetic matroid. And if we have both and they interact in a certain way, then it turns out that it's equivalent to having it come from a matrix.
Okay, thank you.
Sorry, I have a question. Did you say what the strong GCD property is, or is that part of the?
No,
details
I didn't.
Okay.
So this is this is mostly in there because if you look at this only other paper to talk about orientable arithmetic matroids, it gives a different definition and it isn't the same. But what he calls the strong GCD property is what we need. Essentially what it does is it says that to get the multiplicity of any set of columns, we have to look at the bases that those columns intersect. So if it's kind of within a basis, we look at all the ones that contain it. And if it's bigger than a basis, we look at all the ones that are contained in it. And we take some GCD of those, and that determines it. But it kind of comes down to all of the multiplicities are given if we just get the basis multiplicities, which is what we want. But again, it's not important that you know what this means. This is from his paper to do this. And this, yeah. Any other questions?
Just a small one. Do we care what field we're over?
That's a great question. So I'm going to be over R for all of this. And yeah, you kind of have to be over a field of characteristic 0, or else things won't work the same way. But as far as defining matroids, I think there could be other ways of doing it. Like you can certainly define a matroid over any field, but yeah, for this construction, I'm just going to keep it over R for everything. Okay. So next up, I want to talk about standard representative matrices. So this matrix on the left is what we had before, and I have this nice looking matrix on the right, which also satisfies all of these properties up here. So these both represent the same OA matroid. And there's one other nice property, which is that if you take the image of the transpose over Z, they're going to be equivalent. So what you can think of this as, you're going to see this a lot where I say like image over Z of something transpose. This is, you take the rows of your matrix and you take some combination of rows. So it's the lattice that's generated by the rows of your matrix. So some integer combination of these rows is going to give you exactly the same vectors as integer linear combinations of these rows. Does that make sense? And it shouldn't necessarily be immediately obvious why that's true, but hopefully the statement makes sense. And this type of matrix is called a standard representative matrix. In particular, it starts with the identity, and then there's just some other stuff on the right of it. And if we have M generating a rank R matroid, and the first R vectors have multiplicity 1, then we can get a standard representative matrix that satisfies these properties. So in this case, we see that the multiplicity of V1, V2 is 1, and that tells us that we can actually get a standard representative matrix that, that is going to represent the same oriented arithmetic matroid, which is nice because it means if all we have is this oriented arithmetic matroid information, we can write it in this very nice way. And there's an algorithm for this too. And when I say unique-ish, because you can switch rows and make them negative, and then there's some stuff with, you could change the orientation by switching the sign of columns, but we don't really have to worry about that. The main point of this proposition is, as long as we have some basis of multiplicity 1, we can be working with standard representative matrices, and that's going to do a lot of what we want to do. So let me show you how OA matroids can be connected to a lot of other things in combinatorics that we might be interested in. So let's say that we start with a cell complex. We can choose some orientation for our cell complex and then look at a top dimensional boundary map between the facets and the ridges. So in this case, we're thinking of this as a two-dimensional simplicial complex that is just the boundary of this tetrahedron. So this is what we end up getting here as our boundary matrix. It's kind of ugly, but what we can do is we look at the OA matroid that's represented by this boundary map. And we, in this case, this matrix, the first 3 columns form a basis with multiplicity 1, which means we can turn it into a standard representative matrix. And this standard representative matrix is going to look much nicer. So we now have this standard representative matrix that describes the same information as this one up here, as far as orientable arithmetic matroid information. Because we can do this for cell complexes, we can also do it for graphs. So OA of G is a well-defined OA matroid. And I also want to have a connection to regular matroids. So one way that we can define regular matroids is that a regular matroid is an OA matroid with multiplicity 1 for every basis. Usually people don't think of it as an arithmetic matroid at all, but because multiplicity is 1 for everything, we could just get rid of this multiplicity and we still have all the information and announce that it's regular. So there's this really close connection between regular matroids and OA matroids that made them a natural direction to go when I wanted to generalize some of the regular matroid results. And it's also true that for any graph, the OA matroid associated with it is a regular matroid. Usually this is stated as a graphic matroid is regular, which is a classic result in matroid theory. And so if we have a regular matroid, we can choose some basis and rearrange the columns so that we start with that basis. And then we can get a standard representative matrix because we start with a basis of multiplicity 1. Because on a regular matroid, every basis is multiplicity 1. Similarly, if we have an arbitrary OA matroid, as long as it has some multiplicity 1 basis, we can do the same thing. We can put that multiplicity 1 basis at the beginning, and we can do this algorithm that I talked about before and end up with a standard representative matrix. So in a lot of cases, we get a standard representative matrix that we can work with when we want to make statements about more general things. And for now, let's not worry about when they don't have multiplicity 1 bases. There's about 10 different things that go wrong in different ways, and it's interesting, but that'll be for later on in the talk. Okay. So let's take a standard representative matrix. This is just some arbitrary one. There's this other guy, d hat, that we can get by taking negative n transpose, or n is this piece over here, and then putting the identity on it. So the way that we go from d to d hat is we take the negative transpose, and then we take the identity. And these are closely related to each other. So we have our d and d hat that we had before. First of all, the rows of d hat are all orthogonal to each row of d. This you can show pretty quickly because there ends up being two non-negative things, or two non-zero things when you dot product them, and one is negative the other one. So it's nice. D hat represents the dual matroid of D. So people who know some stuff about matroids might be interested in that. Oxley constructs this in his book when he wants to show that the dual of a representable matroid is also representable. And if we restrict D to some set of our columns and then restrict D hat to the remaining columns, the determinants are equal up to sign. So in this case, we have a determinant of 3. And over here, I think the determinant is also 3. But depending on which columns we choose, it might be -3 instead. And what we can do is we can put D on top of D hat, and that gives us an invertible square matrix of this form right here. So we're going to be very interested in this matrix, which I'll call fancy D because this D is kind of fancy. So the Sandpile group of D is going to be z to the k plus r mod fancy D transpose z to the k plus r. So this is also called the co-kernel of this matrix, fancy D. And the way to think about this is you take all of the points in z to the k plus r space, all of these lattice points, and you say that 2 of them are equal to each other, if you can get from one to the other by adding some sequence of rows of fancy D. So if you can go from here to here by adding row 1, and here to here by adding row 2, and here to here by adding row 3, then these 2 points are going to be equivalent in the Sandpile group. And this ends up being connected to other versions of Sandpile groups. So if D represents the OA matroid associated with some cell complex, then this is the cut flow group. And you can read Duval, Klivans, and Martin. They have a much more topological motivated way of thinking about things. So they say things very differently, but it ends up coming up with a similar result of this cut flow group of sigma. If sigma is a graph, then this is actually isomorphic to the traditional Sandpile group for anyone who's heard about it. And this is a subject of the pregame show, which I didn't quite get to this idea, but maybe people saw a little bit of it when I was saying at the end that you can get this type of matrix if you're looking at the edges instead of the vertices. I also have a video linked on my website, so you can look at that if you want to learn more about this, because it's not at all immediate to see why this is true, but they end up being connected. If you don't know anything about the Sandpile group of a graph, you're not going to have any disadvantage in understanding the rest of this stuff. And then also there's an idea of Sandpile group of regular matroids, and this is also going to be equivalent to the usual definition. So this ends up generalizing all of these different ideas of Sandpile group. There's a little bit of a caveat that when you have a cell complex, you got to make sure that you have a basis of multiplicity 1. Otherwise, there's just kind of no good way to define the Sandpile group, but I won't really get into that here. Okay, so let me talk about the OA matroid Matrix-Tree Theorem. So the traditional Matrix-Tree Theorem, well, I guess it's not quite. The traditional one is for finding the number of spanning trees of a graph, but the traditional Sandpile way of thinking about it is that the size of the Sandpile group of a graph is equal to the number of spanning trees. We can get something similar, but a little bit more complicated for standard representative matrices. So here's the theorem, and this is what Duval, Klivans, and Martin proved for cell complexes, but I have it here for OA matroids. So what this says is that the size of the Sandpile group is going to be the sum of the multiplicity squared. And here's an example. So let's say we start with this as our D. Then we look at the multiplicities of the bases, which the bases in this case is every pair of columns. And the multiplicity is just the determinant. If we sum the squares of those determinants, we're going to get 14. And then if you looked at the other definition and you put the D hat on the bottom here and you looked at the co-kernel, you would also get size 14. So this ends up following from the Cauchy-Binet formula, which is how you prove the original Matrix-Tree Theorem. And so this means that if every multiplicity is 1, then the size of the Sandpile group is just the number of bases. So this is an immediate corollary of this higher theorem, but as you might guess, it was proven much earlier. And then this is a generalization of the fact that on a graph, the size of the Sandpile group is the number of spanning trees, because spanning trees of a graph correspond to bases of a graphic matrix. That's a good thing to know when you're looking at matrices. So in this case, we have that these two sets are the same size, but the Matrix-Tree Theorem doesn't give you any way to associate elements of one with elements of the other. So much more recently, Backman, Baker, and Yuen define a family of bijections between the Sandpile group and the bases that has some like natural structure to it. And what I did was extend this to the higher dimensional case. So I found a family of maps from the Sandpile group to the bases such that the pre-image of every basis has size multiplicity of b squared. This is the main result of this talk. So I'm going to leave it for like a minute and let people let this sink in. Everything is on this page, and see if you understand why I want to do this and why this is sort of like a bijection, even though it's not really a bijection.
Well, I have a question. Sort
Yeah.
of, why did you list this underneath Marino's theorem?
So I listed the, I guess it's sort of, the Marino's theorem goes with the Backman-Baker-Yuen case, and then my theorem goes to the top one. So you can say that these two middle parts go together, and then the top and the bottom goes together. But yeah, it's not like part of Marino's theorem or anything.
Yeah, thanks. I was just, yeah.
Yeah, I think I might have just gone against the normal convention of how people format talk, so apologies. Any other questions? Okay. So how did I do this? So I'm going to use something called fundamental parallelepipeds, which the way that you get a fundamental parallelepiped is you start with a square matrix, and you're going to take each column of that matrix, and you're going to multiply it by anywhere from 0 to 1, and take all of the points that lie in that. So this is the same as the Minkowski sum of the columns. There's some people say parallelepipeds are only for 3 dimensions and parallelotopes are for more dimensions, but I've seen it both ways. And we're gonna write this this polytope as pi bullet m. So this is the fundamental parallelepiped. And in order to construct the maps that I want to do, I'm going to associate every basis of my matroid with the fundamental parallelepiped of some matrix. And then all these fundamental parallelepipeds are going to go together and do something cool. So what am I going to do? So I have my matrix D, and I have fancy D up here. And I put a little line here so you can see the top part from the bottom part. And this doesn't make sense because it's so much easier to do this by example. And maybe I'll try my, actually, I'm not going to try to do my pen right now because I need to go to annotate and everything. It's easier just waving the hand around. So the way that I get my parallelepipeds is for each basis, I look at each of the 3 columns. And I'm going to ask, am I in my basis or am I not? So V1 is in the basis. So everything below the line turns into 0. V2 is in the basis. So everything below the line turns to 0. V3 is not in the basis. So everything above the line is going to turn to 0. And we're going to do the same thing for each of these 3 pieces. So the second one, it's the V1 and V3 that below the line becomes 0. And then V2 above the line is going to become 0. And similarly for the final one, we have V2, V3 above the line is going to be 0. And then V1 below the line is 0. And all of this is coming from this fancy D matrix up here. Does it make sense where these parallelepipeds came from? Let me know if you have any questions. So what are we going to do with these? We're going to take their union, and this is what I'm going to call the tile associated with D. So it's these 3 parallelepipeds put together. And it's going to look like this. And actually, a friend of mine made me this for Christmas. So here is my tile associated with that particular matrix. And here's a drawing of it. And so what am I doing with this tile? It's this random like thing that's not even convex. How is this going to be helpful in any way? Well,
So,
first of
Alex,
all,
do you mind if I
yeah.
ask?
Yeah,
in
of course.
that picture, are those, do they have disjoint interiors or are they overlapping somehow?
Yeah, that's a great question. So they have non-overlapping interiors. Yeah, so it turns out it's not easy to show, but I thought it was pretty nifty once I got it. The parallelepipeds have non-overlapping interiors, but the thing that makes it way better is that translating this by integer linear combinations of the rows actually gives us a tiling of r to the r plus k. So this can be used to tile 3-dimensional space. And I can show you how but I need to switch to something else for a second.
Well, he does it. You have to say that was the best title of a slide ever, too.
Thank you. Okay, should work. This is what happens when you get a bunch of them. So I still need to go 3D print some more of them. But yeah, it actually tiles space in this way. Does everyone see the video? I hope it's playing okay.
Ooh. Yes, we can
And
see. Yeah.
yeah, I made this using Blender, which is like a video animation software. So it was, someone was like, oh, you should try using Blender for this. And ended up like eating up a couple afternoons, but I think it's worth it. It's pretty fun. But let's get back to the main talk. Okay, so we have this this best theorem I've ever proven, and then I couldn't help but put a proof in here, but I don't think we're going to have time, so everyone's probably sad. I'm just going to skip through this. I end up using the, and then I'll skip this also. So this is just kind of proving that idea that this tile space. So you can see my paper for how that is proven. It's one of those things that I really enjoyed coming up with it and was excited when I got it. But it's so hard to say in a talk. So it's probably for the best. But anyway, I went on this tangent about tiling space with these things, and maybe it was cool, but what does that have to do with anything I was talking about before? Well, let's find out. So let me remind you of what we were doing. We have this standard representative matrix associated with an OA matroid, and we have our Sandpile group, which is the co-kernel of fancy D, or it's this group right here. So what we want to do is find a map from the Sandpile group to the bases, such that the preimage of each basis is multiplicity squared. And the nice thing about our tiling is because the amount that we, like, not only does this tile space, but it tiles space by shifting it by the rows of fancy D. So that means that each copy of the tile in the tiling is going to, each point on the tile for each copy of it is going to look the same with respect to the Sandpile group. We've got, we really only have to look at one tile, and that's like the fundamental region that we care about for the Sandpile group. I don't know if that was the best explanation. Did people understand what I mean by that? This idea that the points in the tile, if we translate them outside the tile, they're going to be at the exact same point in another copy of the tile. So we only have to look at one tile to talk about this Sandpile group. And the boundary is a little bit weird because the boundary is on multiple tiles. So to deal with that, we're just going to choose a direction and nudge things a little bit in that direction. And we're going to say that you're only like in the tile if you get nudged into it. So the interior points are all good, but the points in the boundary are, it depends which direction we choose. And I have an example in the next slide, so this will make more sense then potentially. But what we're going to do is we're going to have this function where, given our direction, W, we're going to figure out which parallelepiped we get shoved into. So we know that any of the points that get shoved into this tile have to go into one of these three parallelepipeds. So the question is, which one does it go into? And that is going to be the basis that we associate that point with. And the theorem is that as long as we choose our W to be sufficiently generic, then this map is going to have exactly the properties that we want. The size of the preimage is going to be exactly the multiplicity squared of the basis. So let me talk about why that's true. So the simplest case is when K and R are both equal to 1. And in that case, we have our identity matrix is just 1, and then we have to have some equal number on the opposite diagonal that's positive in one place and negative in the other. And if we want to draw our tile, it's going to look like this, where the origin is where the hand is right now. And we have our two parallelepipeds. One is generated by 1001, and the other is by m negative m, m0 and 0 negative m. Just whether you make the below the line or above the line be 0. And so translates of this by linear combinations of the rows of our matrix are going to tile the planes. We can see that if we shift this by 1, 3, we go from like this up to here. And if we shift it by -3, 1, then we go from here to here. So we tile the plane, that's what we like. And then let's look at just one copy of the tile. If we choose some direction, let's say we choose our direction to be 1, 1, then we care about which points go into which parallelepipeds. So 9 of these points are going to go into the bigger one, and 1 is going to go into the smaller one. And these are actually the 10 equivalence classes of the Sandpile group of D. So this is going to give us these 10 equivalence classes. And furthermore, we have our basis of multiplicity 1 is going to get one thing mapped into it. And our basis of multiplicity 3 is going to get 9 things mapped into it. So it's exactly that squared relationship that we are looking for. And if we chose a different direction, then you might notice that the interior points are going to be associated with the same basis, but the points on the boundary might be different ones depending on which direction we're going in. So, but no matter what we choose as our direction, as long as it's not vertical or horizontal in this case, we're always going to get 9 points going into this bottom one and 1 point going into the top one. And so there's also this other thing that I think the most useful aspect of it is that it lets us do more pretty pictures. So what we can do is there's a way of tiling r to the r or r to the k instead of r to the r plus k and still having the same properties. So here's an example of one of the pretty pictures we can get. And what ends up happening is when we go to this lower dimension, instead of just getting one parallelepiped of volume multiplicity squared, we get multiplicity many, each with volume multiplicity. So you'll notice that there's a bunch of stuff with the same color that are all congruent. The number of these of a given color is proportional to its area. So that's kind of an interesting thing that shows up. And we could do the same thing where we nudge it in some direction and see what basis it ends up in, depending on basically like what color it is. And this is also going to tile space. So this is 9 copies of this tile that's going to fill up the plane. And here's another one that I think is very pretty looking. And same idea. It's just you get a whole bunch of different things associated with any basis, and it looks like a weird shape it's not convex. Doesn't necessarily seem like it'd be useful, but it does tile space, or I guess the plane in this case, in this nice way. All right, so I want to just talk about a couple more things. So first off, let's say that we're working with a regular matroid. So it's EB, and then there's like an implied multiplicity that's equal to 1 everywhere. So my result is going to give a bijection between the Sandpile group and the bases, because it's going to associate each one with 1. And I mentioned earlier, Backman, Baker, and Yuen have a bijection as well. And mine depends on a direction vector. Theirs depends on acyclic circuit and co-circuit signatures. But it turns out that they're equivalent. So what they're doing when they're choosing acyclic circuit and co-circuit signatures is they're choosing some chamber of a hyperplane arrangement. And what I'm doing when I'm choosing a direction vector is I'm choosing a direction where all I care about is a chamber of a different hyperplane arrangement that is isomorphic in some sense. So yeah, these are both just choosing chambers from hyperplane arrangements. And if you look at the actual representatives that we get for each equivalence class, they're going to be different, but there's sort of a connection between the two. And then there's the question that everyone's probably wondering about, which is what if we don't have this multiplicity one basis? So we can't turn this into a standard representative matrix. There's some cases where you can't possibly choose like what we want our matrix to look like and have it be canonical. And even when we do, there's no way of saying what D hat should be or fancy D. And then if we try to do sort of the naive thing and take some D and D hat where they're orthogonal, but they don't necessarily satisfy the other properties, our map isn't going to work if we try to just do it the same way. But if instead of working with the lattice generated by the rows of the matrix, if we look at the lattice generated by the columns of the matrix, then we can use that same map we had before, and we end up getting something that does work. And this group, the Sandpile group of fancy D transpose, is the Pontryagin dual of the original Sandpile group. And I'm curious about it because there's sort of, it's less natural to define the group, but my map actually works better on this type of thing than in general. And I've just recently, in like the last couple of weeks, so I haven't written it up or anything yet, realized that I think I can extend even further, where I don't even need orthogonality. I just need some certain relationship between the determinants and get something similar to work. But again, I have to be talking about the lattice generated by the columns instead of the lattice generated by the rows. And it also, some people might think, like, why does it matter rows versus columns? The thing is that we had this orthogonality condition on the rows, but then we're interested in the lattice generated by the column. So it's strange that we care about the rows for one thing and the columns for something else. You don't see that too much, or at least I haven't seen that too much. And yeah, so that's it. Thanks for listening. I have some sources here. And yeah, let me know if you have any questions.
Thanks so much. This is a very nice talk. I'm going to undo screen sharing. Oh, maybe you have to undo
Just
it.
stop share. Yeah, that works.
Yeah. And then we can clap. Thank you. Those are great pictures at the end there. So are there questions?
I was kind of wondering with the pictures you showed, how are you choosing the colors there?
The colors? Yeah, it's a good question. So I tried doing something sensible and like having some gradient of colors or something like that, and it's hard to have enough colors and have it look good. So what I ended up doing is totally arbitrary. Choose colors that look different enough to my eyes and mess with it until I have something that looks good.
But like when you chose to color things of the same color, was that just when they were translates of each other? Yeah,
that is important because those are translates that are congruent and they're associated with the same basis. So the same color is important, but as far as what colors I chose, whether this is yellow or this is pink, that doesn't matter.
Oh, okay, so the number of colors was the number of bases in all of them?
Yeah, the number of different colors is the number of different bases, yeah.
Okay.
I have a question. You mentioned that this is similar to the result by Baker and Yuen about other kinds of geometric bijections. In the case of a graphical, or for the Sandpile group of a graph, I know that there are a couple of bijections in literature that are like algorithmically defined, like the rotor routing process or like the Bernardi bijection. Do you know if those are geometric bijections in this same kind of way?
Yeah, it's a great question. So I think that the Bernardi bijection, so I think that the Backman-Baker-Yuen bijection for regular matroids and stuff was inspired by looking at the Bernardi one. But I think it only works in the planar case. So if you have a plane, you have to work with ribbon graphs when you're doing these graphical bijections. But if you have a planar ribbon graph, then I think that the Bachman-Baker-Yuen map ends up corresponding to the Bernardi map, which I guess when you're planar, that also corresponds to rotor routing, right? But I think non-planar, it's still a little bit of a mystery. Yeah.
Great. If there are no other questions, then let's thank our speaker again. Great. And if
Thanks
people
again
have a
for the
little
invitation.
time, we can now have a little coffee hour. There's a few compliments for you, Alex, in the chat if you didn't see
Oh,
them.
great. Thanks.